Welcome back to part 2 of this case study, in which I will refine a Basalt sample that was provided by a Profex user. In the first part I created a new instrument configuration for the PANalytical Empyrean instrument on which this sample was measured. And what I got from the user was this XRDML dataset. Let's open it in Profex, as well as an Excel file with an XRF analysis of the same sample. So when we are done with the refinement, we can compare the refined chemical composition with the one measured by XRF. The sample was described as an epidosite or as a tholeiitic basalt, but we will not be influenced by this. We will just process the sample as if we didn't know what it was. I usually start by double-clicking the strongest peak. And in such a nice crystalline sample, it's usually easy to find the strongest phase. In this case, quartz. We can accept this and immediately create our refinement project. We will select the new instrument configuration we created in the first part, the Empyrean with the 1D ER detector. And quartz is selected, we click OK, and we get our refinement control file. If we run the refinement, we will see that the fit of quartz is OK, but of course there are a lot more signals than just quartz. So to identify the other phases, I will use the search match module. I open it from the window menu, search match phases. We will only search in the minerals subfolder for now. Then we go to restrictions. I don't apply any chemical restrictions. I have to select the instrument configuration, the same Empyrean configuration and copper radiation. And number of iterations I will leave at 10. And minimum and maximum angle is important. As always, we want to search the lowest angle reflections. They are very unique and usually help finding the correct phases. So in this case, if we clip at 9 degrees, we would not include this one in the search. So I will change the minimum angle to 5 degrees. So we start at the very beginning of the pattern. And I think it's enough to search up to somewhere here, or maybe include this broad one. So maybe stop here at 49.5. We start with a strict unit cell variability. We do not allow anisotropic parameters, but we allow to refine sample height displacement. And all these phases are very crystalline, very sharp peaks, so we leave this at high. Then we can start the search match process. And as you can see, the quartz phase we identified by double-clicking the strong peak, and that was already part of the refinement project, was already added as a pinned phase. So it's already performing a residual search. It's not trying to match the quartz peaks again, but only all the unassigned peaks. The best match is corundum. Let's check this. And indeed, it looks like we have very sharp corundum peaks. It's no surprise because corundum was actually added as an internal standard. So we definitely have corundum. We pin it. Graphite always very strongly correlates with this strong quartz peak. So whenever we have quartz in the sample, it also thinks that graphite matches this strong peak because graphite doesn't have a lot of other peaks and they are much weaker. So this is usually a false positive if we have quartz in the sample. Then clinochlor. This is interesting because it matches this very low angle peak. That doesn't look too bad. We could keep it. Muscovite, probably not. We would see something here. And then we only have red, poorly matching phases. Now if we run another residual search, I want to run it in the BGMN folder with 400 mostly mineral structures. It will take a long time to run through all 400 structures, but I will speed it up a lot, so you will not have to wait. And let's see if it finds more matches in these 412 structures. That was slow. This has taken about 12 minutes in real time. Let's see what we got. The best matching phase is epidot. And as we can see, it matches most of the strong peaks quite nicely. This one, the duplet here, all these. So that seems to be a perfect match. What about Dickheit? Seems to match mostly this one here. But this is already a Kleinochlor peak, so we probably don't want another phase here. Kleinozoisite seems to match most of the ones already matched by epidot. So we will just accept epidot, and this should give us a fairly nice coverage of most of the peaks we measured. So now, in addition to the one we already have in our project, we matched corundum, Kleinochlor, and epidot. Let's add these to the project and see what a real refinement looks like. So we select the Add Remove Phase dialog. All these matched phases should be pre-selected, epidot, Kleinochlor, and corundum. Okay. Now they are added to the project and we can run a real refinement. And it looks pretty good, but if we zoom in here, we still have at least one phase we have not identified yet. But this one we will try to identify just by double clicking, because the search match takes so long. If we double click here, it says calcite. We have a second peak here. So that looks pretty reasonable. Let's just add calcite and run again. Very good match. Now there's one more peak here and a small one here. Now if I double click this one, it suggests a feldspar, plagioclase. Let's scale down the peaks a bit. We can try and add this plagioclase. And then we have this very small peak here. It's rutile. Rutile also has a peak here and here, but we don't see any signal. So I'm not quite sure if this actually is rutile. We can add it and see if it is refined to 0 weight percent. If it goes down to 0, we will just remove it from the refinement. It's starting to look quite promising. Rutile, feldspar here. So I think we have identified all the phases. Now we need to optimize the refinement. First of all, we can see that the profile of these Kleinochlor peaks here and here is not very good. Also intensities, this is also Kleinochlor. So we should do something about that. And the rest looks already quite good. One thing I like to do to check if the refinement is stable, I go to the list file and I scroll through all the phase parameters and I check if they all have an estimated standard deviation. I explained this in one of the previous case studies. Here with the plagioclase, we have the A and B cell parameters, the alpha and beta angles. So what happened here is they were blocked by the upper or lower limit we provided in the structure file. So in the plagioclase structure file, We set limits for the A parameter. It was refined, but we set limits. The A parameter is here. And it was indeed blocked. So we applied a restriction that was too strict. And that's why it does not have an estimated standard deviation, because it was not refined freely. It was blocked by our limit. So if the signal is strong and well defined, we can try and either increase the limits or even remove the limits. And the plagioclase signal is one of the weaker ones, but we do have peaks at these positions. We can just increase the limit quite a bit. We do it for A, B, and alpha and beta. There are no rules by how much to increase them. Just do it step by step and check if the refinement is still stable. So we run it again. Let's check the list file again. They all found a stable solution. It is actually not a surprise that we had quite some shift in the unit cell of plagioclase, because we just picked one of them. If we look at the phase diagram of the feldspars, we are somewhere here. So oligoclase with only 16% anortite. This is the one we picked, but maybe it was not exactly the right composition of feldspars. So maybe we were more on the anortite side or on the albite side. And of course, the unit cell will change, will shift quite a bit if we change the composition. So we started here, but we maybe after the refinement, we ended somewhere else. And this is the refined unit cell, which can be quite a bit different from the starting values of this plagioclase composition. So now we should go back and check this clinochlor refinement. We have still problems with shape and intensities. Maybe it's not the best choice of the chloride minerals. We could just try and replace it with this one and see if we get a better refinement. We can check the chi-square value, 3.93, with the previous, with the clinochlor phase. If we replace it with chloride and check if we get a better fit, we will just keep chloride. If not, we go back to clinochlor. So let's add chloride and remove this one. And we can run it again. The peak positions of clinochlor were quite good. They matched well with the measured peaks, but the intensity were totally off. Clinochlor is the triclinic phase, but now we are using a monoclinic chloride phase, and now we get much better fits. So this is the better choice. We can also see chi-square went down from 3.9 to 2.58. Quite a significant improvement. Also the difference curve starts to look very good. The beta angle was blocked, so we should increase the upper limit. We can afford to release some more profile parameters. Currently we are refining texture with the lowest possible model, second order, and we are refining anisotropic crystallite sizes. We could just try and refine microstrain. Probably doesn't help much because the profile fit is already very good, but we can still try. We need to change the profile function from number 3 to number 4. Number 3 only knows crystallite size peak broadening. Number 4 also knows microstrain, which is refined with the K2 parameter. And now I set it to isotropic refinement. And we could increase the texture model, but we already get a pretty good fit, so it's probably not necessary. Chi-square parameter is again a little bit better. So chloride is probably as good as it gets. Let's have a look at the quartz. We are currently refining isotropic peak broadening from isotropic crystallite sizes. We could also try and refine K2 microstrain. It's only a marginal improvement. So quartz is done. What about epidot? We are refining isotropic crystallite sizes. Epidot is a very strong signal. It's probably the main phase. If we have a look at the quantification, we have 52% epidot at the moment. It's probably not the final result, but it certainly is the strongest phase. And the profile refinement looks fairly good. But since it's a strong phase, I will just try and see if we get improvements if we refine microstrain. That was a surprisingly strong improvement, so there seems to be microstrain. Other than that, there is nothing much to do. Then we have corundum, the internal standard. It's a strong signal and a very crystalline phase. Although we do have overlap here with one of it's the epidot phase, but that's the only peak of corundum that overlaps so strongly. These are fairly isolated. We can also try and refine microstrain. And then we have calcite. There's almost only one peak visible, this one here. We are currently only refining crystallite size isotropically, but since the signal is weak and it's only one peak that is actually well visible, I will not refine more than that. Then for plagioclase, we already refine both the crystallite size and microstrain, so I will leave it. And then we have rutile, the last phase. This is only this extremely weak peak over here. So I will certainly not refine more. We only refine the crystallite size right now. So with these new profile refinements, we can run it again. And that looks pretty good. We have a chi-square value of 1.77. And if we look at the phase quantities, about 18% quartz, 49 epidot. Corundum was added in 20% as an internal standard. We refined 20.67, a little bit more, so there's a small amount of amorphous phase. Calcite is only 2%, plagioclase around 4%, rutile is less than 1%, and chlorite is 5%. Now there's not much we can do to improve the refinement. I'm not so happy with this single rutile peak here. I think there should be a bit more than this 0.36%, maybe twice. That is about all we can squeeze out of this dataset. Now, since we have an XRF analysis of the same sample, it will be interesting to compare the refined chemical composition with the XRF data. We can look at the refined chemical composition by opening the chemical composition window from the window menu. It probably opens as a tab here behind the refined parameters. First, we have to select the quantity goals that belongs to chlorite. It's the Q chlorite. Same for epidot and plagioclase. The other ones were detected automatically. I will undock this window and increase the size so we see more. Now we see the refined phase quantities in weight percent. Here it's normalized to 1, but here in this window it's normalized to 100. And then of each element, we see the weight percent. Now we don't want to compare element weight percent, but XRF data is reported in oxide weight percent. So we have to change in the settings how these weight percent are presented. We go to Edit, Preferences, and here we have the chemical composition. And then we change the composition to elements, to oxides by weight. And click OK. And now we have to run the refinement again. Or we could also just close and reopen the project to change this table. And now you can see that we always get the oxide of each element instead of the element itself. Now before we can compare these oxide weight percentages with the XRF analysis, we have to eliminate the corundum from the calculation because the XRF analysis was done before the internal standard was added. And we have to do this in Excel. It's not very complicated, but I will export this table to Excel. So I go to Results, select Export Chemical Composition of this project. We only have one. And I save it in the project folder. Then I go to my current project directory. This is the exported chemical composition. I have to split the cells at the semicolon character. So I go to Data, Text to Columns, still limited by the semicolon. Now I have one column with the file name, the sample ID, the phase quantity, and each oxide in weight percent for each phase. Now I have to rearrange this a little bit. I will speed it up. I want to have the same layout as in the Profex table. Now I have calculated the total oxide composition again, but what I actually want to do is I want to calculate it without the corundum. So all I have to do is delete corundum. Now this is all set to 0. Now I get the composition without corundum in weight percent. And this can now be compared with the values we got from the XRF analysis. Now this is the final comparison of the refined oxide composition with the XRF results. We overestimated the silicon content a bit by 6%. We underestimated titanium, which was already expected because the rutile peak was also underestimated in the refinement. The aluminum content is very close. The iron content was a little bit underestimated. Magnesium content is very close, same for calcium. We overestimated sodium a little bit, and these two were not quantified by XRF, but they measured the loss on ignition. There were some volatile constituents. So all in all, with the exception of an overestimation of the silicate content, it is a quite good agreement. Of course, the composition of the feldspar, of the plagioclase, might be different. The one we used was fairly rich in sodium, maybe it was more calcium rich in reality, or even maybe there was some potassium. We did overestimate the sodium content a little bit, so that might be an indication we underestimated calcium. So if the true composition of the plagioclase was a little bit more towards the anortite end, we would be even closer with the calcium and the sodium content. That was an interesting example because it allowed us to compare the refinement results with the XRF data. Big thank you to the user who provided this data, and also the information on the Empyrean instrument, the pictures we used in the first part of this tutorial. I hope you enjoyed it, and I hope you learned something. And if you have any comments or questions, let me know in the comments below. And I hope to see you for the next video, which will be released soon. Have a good time. Bye bye.